Hello everybody, Sean here from SMD Methods. You're very welcome into this second video of what I intend to be a three-parter, in which we'll use a classical Runge Kutta solver to find the solution to a second order ordinary differential equation, which models a spring mass damper system. Now the problem is taken from problem 25.16 of Numerical Methods for Engineers, edition 8 by Stephen Chapra and Raymond Canale. In the first video, we finished off broadly with this screen in which we wrote out the Runge Kutta algorithm, or the Runge Kutta expression for finding the next dependent variable value given a current dependent variable value and an adjustment to that. We've seen in these that we have slopes, and in this second order equation, which we have decomposed into two first order equations, we'll have two sets of slopes, k's and l's. And then we had finished off the video with writing out what the input values were for both the independent and dependent variables, which are to be plugged into each of them functions. So without further ado, moving into the content for this second video, I'm going to maybe swap over here into my tablet so I can do some writing. It was working on Bluetooth up till very recently, but not anymore. So what we now need to do is we need to determine a step size, okay, h. Now we are solving this with respect to time, dt, so that means our step size is not going to be a spatial step, it is going to be a time step. So we have also been asked to solve from t is equal to 0 to t is equal to 15 seconds. Big question will be, what is an adequate time step, or what is an appropriate time step? Well, for classical Runge Kutta, it's very important that our time step is not too large. Classical Runge Kutta, or RK4, is not as susceptible to larger time steps as, for instance, Euler's method is, which is a first order, or indeed Heinz method. However, we don't want it to be overly large. So what I'm going to propose for this one is h for step size is equal to, we can go 0.1, 0.2. I'm going to go for 0.2 in this. Now, of course, for this video, I'm only going to run through one iteration to calculate my new velocity and position values at t is equal to 0.2 after one step size having previously been at t is equal to 0. And then I'm going to move on to MATLAB and we'll run the full domain, or the full interval from 0 to 15 seconds in a loop. So it'll be much handier. So we're going to say h is equal to 0.2. We'll write in our parameters here as well. The mass, I recall, to be 20 kilograms. By the way, 0.2 will be in seconds. 20 kilograms. Our damping coefficient, I'm going to set that up to be 40, which was the critical damped value. Of course, that's Newton seconds per meter for a unit. And then our spring constant was 20, I believe. Of course, that's newtons per meter. So bear in mind that this k is a spring constant. It has nothing to do with these k's here, which are slopes. All right. So having known this, what we're going to do is we're going to calculate out our k1, l1, k2, l2, k3, l3, k4, l4 for each of the functions. So the k is attributed to the f function, and if you recall, the f function was giving me dv dt. No, it wasn't. It was giving me dx dt. dx dt was my function value. So if you just bear with me, I'm going to swap back to my mouse so I can do some scrolling. Just in case you missed that detail in the first video. There we are, dx dt was v, which was what my function value is. So solving dx dt, solving my f's, I'll be getting an x value. So when I'm looking for my x's, I'm going to be using my f function, which is attributed to the k's. And of course, solving dv dt, which is my acceleration, is this function here. I'll be looking at the g function, and the g function, having solved that, it'll give me a v, which uses my L slopes. Okay, so let's calculate out K1 first. I'm going to go back to my tablet. K1. K1 is just a function value of t, v, and x, my current t, v, and x inputs. So let's say, let's solve for K1 and L1. Right? So our inputs for them, inputs are going to be in this order as well, t, v, and x. I can just about get some more space. It's a t, not a 6. And the t is at 0 time. The velocity at 0 time is 0, and the x at 0 time is 1. K1 is equal to the function value, is equal to, well, the function itself at 0, 0, and 1 at these values here. The function f is equal to v, right? That's what it is. Means that I'm only going to use the v value. So here, K1 is equal to 0. That's it. Shouldn't even put in a full stop there. Now, L1 is going to be slightly more involved. L1 is equal to the g function. L1 is the g function using these inputs, 0 for t, 0 for v, and 1 for x. Our function for L1, our g function, is 1 over m. I'll tell you what, I'm going to just put the value straight in, maybe to save a line, if nothing else. And it's also minus 1 over m. M is 20. So if you cannot recall that, you can look back up at the top there and see what the g function is. 1 over 20 multiplied by c, which is 40, multiplied by v, which is 0, plus k, which is 20, spring constant k, nothing to do with the slope, multiplied by x, which is 1. So therefore, L1 is equal to minus 1 over 20 multiplied by 40 by 0 is 0, plus 20 by 1 is 20, which leaves there that L1 reduces down to minus 1. So K1, let me put these in a slightly lighter shade of red. One might call dark pink. Okay. K1 and L1. Lovely. Now, for K2 and L2, you'll notice here that I need to make adjustments to my independent and dependent input values. My T input, I must adjust my current T value by adding on half a step size to it. I must adjust my current V input value by adding in this height, which is given by half a step size, which is a rise multiplied by a slope. So or a run by a slope gives me a rise. The slope I'm going to use is going to be the slope that was determined in the previous step. For V, it's the slope that's been determined there for L1. And of course for X, I'm going to adjust that by 1/2 of H by K1. So let's see if I can pick up my cursor here, or my slider, which I can. So what I'll also do is I'm going to underline this in that same color, just so we can keep a track, maybe a wee bit easier, of where we are. Let's now solve for K2 and L2. So our inputs are indeed our T plus 1/2 of H, our V plus 1/2 of H multiplied by L1, and then our X plus 1/2 of H multiplied by K1. Now, questions that my own students come back to me very commonly with is, how do you know to apply the L1 to the V here and the K1 to the X? Why don't you put K1 onto V? How do you know that? Well, the input values for these are going to be, this is dv dt. When you solve dv dt, you get a V. And we've seen up here that our dv dt is the g function, right? So this is it here, the dv dt is that g function. And then the g function that we're using, when we solve that, we get a V, are the L's. It's just, it doesn't really matter. It's just that the standard Runge Kutta 4 convention, I believe, or the nomenclature or the choices of letters to represent functions and their inputs. F and K is the standard one if you only had a first order differential equation. And that's given in numerical methods for engineers and a lot of other sources. F and K go together. Now, if you have a second function and its slopes, if I go F and I go up one letter to G, it's a different function. It's going to have different slopes. So I'm at a K, I'm going to go up one letter to L. So F is to K, G is to L. The G function, when I solve that, I get a V. So I'm going to adjust all my V's by the L's, because the G and the L's go together. The F function is dx dt. When I solve, I get an X. So I'm say my X's, right, are attributed to the F function, and the F function slopes are given by the K's. So I adjust the X's by K, adjust the V's by L's. And that's how I would propose we look at this now. Maybe someone can propose to me how I get the cursor back or the slider. Had it there a second. This is probably going to take more time than making the video, folks. Apologies, flicking back and forth. But eventually we will get there. And I'll slide back into here again. Right, so there's my inputs. So let's see, can we work out values for them? T is 0 currently. Current time step is t, plus 1/2 of 0.2 was our h. Our v is 0 plus 1/2 of h is 0.2 times L1 is minus 1. And our x is 1 plus 1/2 of h, which is 0.2 multiplied by K1. I believe K1 was 0. 0. So what do we have? What's our T input value? Our T is 0 plus half of 0.2 is 0.1. Our V input value is 1/2 of 0.2 multiplied by minus 1 is minus 0.1. And of course our X value is going to be 1 plus 1/2 of 0.2 multiplied by 0, which is just 1. So our K2 value is equal to, we're going to use our function f using 0.1 minus 0.1 and 1. I didn't write it up here, but that's this function here is just equal to v, right? That's all it is equal to v. So our v value is this middle one, minus 0.1. So we can say now that K2 is equal to minus 0.1. Right? Let's go for purple on this one. That I'm going to solve for K2 and L2. Just color code these again. Now L2 is equal to, this is our G function, right? And we're going to be putting in the exact same inputs, minus 0.1 and 1. and that there is equal, that was equal to V over, this is equal to 1 over M minus 1 over M by CV plus KX. Oh, let's go for it. L2 is equal to minus 1 over 20 multiplied by C was 40. Our V input value is minus 0.1 plus our K value is 20 plus our current X value is 1. So there is no T inputs in either of these equations. Okay, let's go on down and see, can we figure this one out? L2 is equal to minus 1 over 20. Let's open up a bracket. 40 multiplied by minus 0.1 is equal to minus 4 plus 20 multiplied by 1 is 20. It's equal to minus 1 over 20 multiplied by 16. And then L2 is equal to minus 0.8. So 16 over 20 is 4 over 5. 4/5 is 0.8. Of course, it's a minus number. Lovely. They're solving for K2 and L2. Now, let's move on. Let's solve for K3 and L3. And let's go with a different color now. Blue. And so our inputs are going to be the identical same as the inputs for K2 and L2. The only difference is instead of using L1 on V and K1 on X, we'll be using L2 on V and K2 on X when we're solving for K3 and L3. So what we're always doing is we're using our most recent slope. I'm not going to bother taking all that. I'll just take this bit here. Control C. So can we get ourselves down here somewhere? Control V. And let's try it in there. So let's see, can I just get this kind of more into the center? So I'm not going to use L1 and K1. I'm going to be using L2 and K2. So T stays the same. This minus 1 that was in for L2, we need to change that. That becomes minus 0.8. 0.8. And then our K2 value is no longer 0. Our K2 value is minus 0.1. See up here. Okay, so this is going to stay 0.1 obviously, because we haven't adjusted it any. And then let's see, can we work out values here for our new input value for V and new input value for X. So 1/2 of 0.2 is 0.1. 0.1 multiplied by minus 0.8 is going to be minus 0.08. This one here, 1 plus 1/2 of 0.2 multiplied by 0.1. Half of 0.2 is 0.1 multiplied by minus 0.1 is minus 0.01. Take 1 off of that and we're at 0.99. Let's double check that's 0.1 by 0.01. Yep. I'm going to be engaging MATLAB here anyway, so let me just double check that. It's only 5 o'clock, but it's been a long day. 0.1 multiplied by 0.1 is 0.01. Yeah, and then 1 minus the answer, and that is 0.99. Happy enough. Apologies for that very elementary check and doubt, but better safe than sorry. Measure twice and cut once, as everyone says. So our K3 value, just to keep the same nomenclature, I wrote it in as being my function value at these inputs, 0.1 minus 0.08, 0.99, that there is equal to v. Right? That's the function value at them values, at them inputs. So the only value that's applicable is minus 0.08, which is my v value. So K3 is equal to minus 0.08. Doing this in blue, so I'll box it off in blue. Lovely. Now, L3 is equal to my g function using them same inputs of 0.1 minus 0.08 and 0.99. That's equal to 1 over m multiplied by c by v plus k by x. And go for L3 is equal to minus 1, m is 20. So can I bring this down, center it up a wee bit. 1 over 20. And let's multiply into that my c value, or RC value, be inclusive here. These are all in this with me. 40 multiplied by our v input, which is minus 0.08. Incidentally, be careful that you don't cross up where your x and your v values are. All right, so if we chose to put v first, make sure you choose the right one. Again, make sure the independent variable, I've said it a couple of times, is always the first one you put in, and then the dependent variables come after it. And it's not critical to the extent of my knowledge what order you put the dependent variables in, so long as you remember the order. 40 by minus 0.08 plus k. Suppose you could say the same about putting the independent variable in last. Once you remember it's last, but convention shows the independent variable in first. And then my x value here is 0.99. All right, let's take it down a wee bit. Minus 1 over 20. 40 by 0.08 is 0.3 minus 0.32 maybe. Let's just check that there. Minus 0.08 multiplied by 40 minus 3.2. And then 20 by 0.99. 19.8. 19.8, I'm going to take 3.2 away from that. So let's go for answer minus 3.2, 16.6. It's equal to minus 1/20th of 16.6. That leaves there that L3 is going to be equal to answer divided by 20th of that, 8.83, which is of course a minus 0.83. Okay, so there we go, L1, L2, L3, K1, K2, and K3. Now let's solve finally for K4 and L4. Put down this one here. Solve for K4 and L4. All right, let's go green. Okay. Our adjustment values on these are inputs. Are slightly different from the K2 and the K3s, and that we're not using half step sizes now, but we're using full step sizes. So just to keep the convention the same, I put inputs and then I put an arrow, I open the bracket. This is going to be T plus H. The V, which I have coming next, second, is going to be plus H multiplied by slope for V, which is the dV/dt solution, which is the G function, which are the L's, L3, and then X plus a full H by K3. Right, so values for them, 0 plus 0.2, v, my current velocity value, my initial value, given that I'm still on the initials at my first time step, is 0 plus 0.2 by L3, which is minus 0.83. And x, this one here, is 1 plus the h. The h value is 0.2 multiplied by a K3 value minus 0.08. So again, conventions. Yeah, of course, just work out the values. 0 plus 0.2 is 0.2. 0.2 multiplied by 0.83 is going to be by 0.0166 minus 0.0166. Just double check that into MATLAB here. 0.2 multiplied by 0.83. 0.2 multiplied by 0.83, 0.166. 2. Of course. Good job. Check that. 166. Yep. And then this one here, 0.2 multiplied by the minus 0.8 plus 1. Let's write this all in as one function. MATLAB 1 plus 0.2 multiplied by minus 0.08 equal to 0.984. Okay. So K3, this is for K4, is equal to the f function using 0.2 minus 0.166 and 0.984, and that there is equal to my v, is what the f function is. And the only v value that I have, the only thing I have to plug in, the only input I have is a v, and this is my v value minus 0.166, which means there that K4 is equal to minus 0.166. And that's in green. All right, L4. L4 is equal to the g function, and we're using 0.2 minus 0.166, 0.984, and that there is equal to minus 1 over m by CV plus kx. And so L4 is equal to minus 1 over 20 multiplied by C, which was 40, multiplied by my current V value, which is minus 0.166, plus my K value, spring constant, which is 20, multiplied by my X value, which is 0.984. L4 therefore is equal to minus 1 over 20. And let's see if we can work out what we have in the brackets here. In our first place, I have 40 multiplied by 0.166, negative 6.64, be minus 6.64. This is going to be a positive number, 20 multiplied by 0.984. 20 multiplied by 0.984 is equal to 19.68. So therefore L4 is going to be equal to that there. So let's go back to MATLAB and let's go for answer minus 6.64, 13.04. Of course, we need to divide that then by answer divided by 20 over m. Yep, 0.652, which will be a minus number as well. Minus 0.652. That's in green. Okay, so there is K1, L1, K2, L2, K3, L3, K4, L4 worked out. All that's left to do now is to plug them into the relevant equation. So let's solve for our V first. No particular order, it's just that V came before the X in this list. So in the V here, this is the dv dt, this is the G function. The G function uses the L's. So I'm going to be using the L slopes for this one here. Okay, let me see, let's move these here out. And if there is any chance, there we go, cursor back, please. No cursor back. So what we'll do here now is work out our new V value, where V of I plus 1 is equal to my current V value plus 1/6 of the average of the L slopes, which is L1 plus 2 L2s plus 2 L3s plus an L4 multiplied by my step size H. So at say t is equal to 0.2, my first step size, vi plus 1 is equal to what my current size was at t is equal to 0, which was 0 plus 1/6 of. Let's keep my mouse click on the cursor. Minus 1 for L1, minus 0.8 for L2. I have minus 1 plus 2 times minus 0.8 plus 2 times L3, which is 0.83 minus 0.83 plus an L4, which is a minus 0.652, all multiplied up by H, which is equal to 0.2. So V of I plus 1 is going to be equal to, so let's see, can we just write this out as a straight line function in MATLAB, minus 1 plus minus 1 plus 2 times minus 0.8 plus 2 times, let's see what came next, minus 0.83 plus, I'll just put this straight in as a minus, this is a single value, 0.652 minus 0.652. Equal to that. Answer multiplied by my step size, 0.2 is equal to that, and then answer divided by 6 is equal to minus 0.1637. So that there gives me my new velocity, which maybe there's an error in it. I wouldn't like to think that there is. We're careful enough on our calculations, but outside of giving a huge amount of scrutiny to it, it is sensible in that the velocity, again being a vector and having a minus value, shows that it is moving to the left in the negative x direction, which makes sense because it was in a state of inequilibrium in a positive direction, which means that it has to move in the negative direction to regain equilibrium, which the velocity is certainly showing that it is returning that way. Now the rate of return, we could look into that. Would certainly need to check that one to make sure that it is correct. But yeah, hopefully Hopefully we are good. Remains to be seen. We'll check it in MATLAB. Next one is for x. X of I plus 1 is equal to x of I. So this is the dx dt function. Dx dt is our f function. Our f uses our k slopes, which will be 1 over 6th by k1 plus 2k2 plus 2k3 plus a single k4 multiplied by 0.2, which is equal to x of I. Our initial x value is 1 plus 1/6 of k1, k2, k3, k4. K1 was 0, k2 is minus 0.1, k3 minus 0.08. So it is 0 plus 2 times minus 0.1 plus 2 times minus 0.08 plus the k4. I'm just going to scan k2 and k3 brave and quick. Minus 0.1 minus 0.08 minus 0.166. 66, that's a minus by 0.2. So let's try this again into MATLAB as best we can. So I'm going to just ignore the 0, the naught. I'm going to go from here on in. So let's go into MATLAB. Let's go for 2 multiplied by minus 0.1 plus 2 multiplied by minus was it not 88? Yeah, not 8. Not 8. And then this one here was a minus. And this one took us into minus 0.166. Gives us 0.526. Answer multiplied by 0.2, which is our step size. That gives us our adjustment. And an answer there divided by 6. It's in our slope, minus 0.0175. And our answer then plus 1 is equal to 0.9825. 0.9825. And that also makes sense because we could see our initial value for x at t was equal to 0 was 1. We were out of equilibrium to the right, which means and we're moving in the negative x direction, which means that our x value should be less than 1. They should be approaching 0 and pass 0 into the negative side, which two of them make perfect sense there at the minute. So what I propose to do, well, what I'll do here first actually is just to make sure that I'm not leaving anybody in the lurch. And if you did want to carry or continue on with a kind of a written workflow, that you know where to go. If you recall there at t was equal to 0, right, we had v was equal to 0 and we had x was equal to 1. At t is equal to 0.2, which is t is equal to t of I minus 1 plus 0.2, my step size. Now v is equal to minus 0.1637. And x is equal to 0.9825. Right? This is where we are now. So this is now current. Right? This one here is now current. And this is where we use to launch into our second iteration. So for second iteration, we start at t is equal to 0.2 and step 0.2 t plus h, which is 0.2 plus 0.2, which is equal to 0.4. So I'm stepping out to 0.4. And what I'm going to do is I'm going to calculate K1, K2, or K1, L1, K2, L2, K3, L3, K4, L4, given my new t values, which are broadly irrelevant, given that there's no t's in the f or g functions. But certainly my new v values and x values will be very important. So the next step will be to calculate updated K and L slope values using the current, new current, it's just current, using the current, I keep an independent and dependent variable values. So for example, K1, just going to keep again the same kind of writing that I had up here. Solve for K1 and L1. I'll just do K1 and L1 and then we'll leave it. So solve for K1 and L1, right? We know that K1 is going to be equal to the function value at some t value, some v value, and some x value, right? So our t inputs here, and that there is equal to v. So it's equal to some function value. And my t value, current, is 0.2. My v value, current, is minus 0.1637. My x value, current, is 0.9825. So K1 in this case is equal to my current v value, this is the v, minus 0.1637. Right? Then L1 is going to be the identical same, except it'll be the g function, 1 over m by cv plus kx quantity. The K2 function, we're going to have adjustments. It'll be t plus 1/2 of h, so it'll be 0.2 plus half of 0.2, which is 0.1. So our t input will be 0.3. Our v will be this v value, our current velocity value, minus 0.1637 plus 1/2 of h, which is 0.1, multiplied by our L1 value, and our x is going to be our current x value plus 1/2 of h multiplied by our current K1 value. All right, and that will take us along the same sort of, I won't say trajectory, but it's definitely the same sort of workflow as what we'll have here, K2 and L2. Here I was using zeros, or sorry, here I was using my current values. For t was 0, v was 0, x was 1. These next ones I'll be using 0.2 minus 0.1637 or whatever it was, and x 0.98 odd. Okay, so that's just how we update it, and we get new K1, L1, K2, L2, K3, L3, K4, L4. Plug them into the Runge Kutta formulas, which is going to be my new velocity value is equal to my current plus 1/6 of all 6 of the slopes, 1K1, 2K2s, 2K3s, a K4, multiplied of course by the step size. And then you get new values and so on, marching forward in time. So that is how the, that's how the, get this going here now again, please, come up. There it goes. It's gone again. Unreal. And that's how you progress through, just marching forward, in this case, in time. All right, so what our next step is going to be on this, I'm just going to write it in here. I'm going to continue to solve in MATLAB. All right, so let's go on to MATLAB and I'll tell you what, it's 45 minutes in. I'm going to stop the video here and I'll start my third video then in a little while, and I'll open that up with the solution in MATLAB. We'll run a loop and see can we get our position and our velocity values from t is equal to 0 up to t is equal to 15. And then what we'll do is we'll open up SimScape and we'll model it in SimScape. Solve it using Runge Kutta 4, of course, classical Runge Kutta. Look at the graph, compare, and then what we may also do is solve it using ODE45, which is Dorman Prince, which is different from Runge Kutta in that Dorman Prince is a variable time step, Runge Kutta is a fixed time step, and look at how that solved it, any sort of differences in the outputs, and we'll have an evaluation as well as the computational effort. C is a fixed time step, more appropriate for solving a very simple spring mass damper system, or do we need to go into something as detailed and as, I suppose, relatively more complicated as ODE45 or Dorman Prince. So hit the subscribe button, because when the next video does come out you get a notification, so hopefully you'll be on the edge of your seats till that happens. But if not, I hope you do find the time to come back in and have a look at the MATLAB and the SimScape solutions to it. Yeah, hope to see you in that one. Thanks very much.